All right, this should be what, Chem26BBlake. And if you got this explanation of what was going on with pi bonds and sigma bonds and double bonds and triple bonds and single bonds in one shot, that would be very unusual. So you should have questions. So ask more than once if you have to. It's not easy to grasp. Okay, going onward to something that's probably a little more familiar and a little easier to grasp. Let's go, first of all, section review, page 247, 7 and 13. Identify the type of atom that normally or generally conforms a covalent bond. It's usually between two nonmetals. Most covalent bonds form between two nonmetallic elements. Number 8, describe how the octet rule applies to covalent bonds. When elements are covalent bonding, they're usually trying to get 8 valence electrons by sharing. Atoms share valence electrons. The shared electrons complete the octet of each atom. Most of the time, it's 8. Sometimes 6, sometimes 4, sometimes 2, sometimes 10, sometimes 12. Most of the time, it's 8. Illustrate the formation of single, double, and triple covalent bonds using Lewis structures. Okay. Single bonds with a methane. I'm pretty sure I have this on the next page, so. Yeah, methane, I've got carbon, hydrogen, 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 1 electron each for hydrogen, hydrogen, it's methane, 4 of them. 4 electrons with carbon, so you just put carbon in the middle, hydrogen around it, shared pairs, and once you put the shared pairs in, it's just a matter of putting sticks in. It's done. Because this total is 8 and this total is 8. So there's your methane, CO2. Those are all single bonds. Okay, now we got double bonds in the carbon. I mentioned that in the last video. If you have CO2, you have carbon with 4 electrons, oxygen 1, 2, 3, 4, 5, 6. Oxygen 1, 2, 3, 4, 5, 6. That total was 16. Put the carbon in the middle, oxygen on either side, put it in the shared pairs, then give everybody 8 if they get 8, and they do. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. This total is 16, 18, 20. That's too many. So I'm going to take this pair out, move this pair in, take this pair out, move this pair in. I can take. It's easier if you take them off the central atom. Once I do that, I have a carbon, 2 shared pairs, an oxygen with a pair and a pair, 2 lone pairs, 2 shared pairs, oxygen, like that. So when you're done, double bond, carbon, double bond, oxygen, this is what you have. Okay, for a triple bond, use the Lewis structure to demonstrate a triple bond. Hopefully you're pausing this as you go through if you need to. Got an H and a C and an N, there's 1, carbon's got 4, nitrogen's 5. Remember how we do that. At least this part I think everybody's got down. Nitrogen is up here. Has 5 column, takes 3, but it's going to share 3 because we're talking about covalent bonds. Oops, wrong thing. Okay, that total is 10. Put the carbon in the middle because it almost always goes in the middle. Shared pairs, then give everybody 8. 2, 4, 6, 8. 2, 4, 6, 8. Hydrogen only has 2. That's 8, 10, 12, 14. That's 2 pairs, too many. So if you take them off the central atom, it's easier. Just take them off the carbon, move these in, move these in. Once I do that, and H, whoops. Well, we can do it that way. And when I replace that with sticks, that's what we have. Hydrogen cyanide ion. That's what they used in the gas chambers in Auschwitz and other places. Okay, so that's how you show single, double, and triple bonds. Okay, next question. Compare and contrast ionic and covalent bonds. Well, there was a big table in probably the last video. I said, this is real important and you gotta know this. Where was it? I don't know where it was. It was probably back in week 4. Valence electrons are involved in both types of bonds. In covalent bonds, the electrons are shared. In ionic bonds, they are given and taken. They are transferred. Do you know that from last year? I don't know how many times we said that. Mostly you people got that down. Sigma bonds and pi bonds. Contrast them. Show the difference. Okay, sigma bonds are going to be a single shared pair. Covalent bond. Direct overlap of orbitals. A pi bond is when you have p orbitals overlapping. Above and below parallel overlapping p orbitals. You can have p orbitals. No, I guess not. I don't want to say that. It's true, but it'll have you confused. So let me just go with what it says. A pi bond is the parallel overlap of p orbitals. So going back to this one. I don't have a nice good drawing of that. That's the thing. I don't want to have one I'm happy with. Oh, I know where there's one. It's in the organic stuff. Right here. Back here. Here it is. Right here. Oh, nice diagram. Edit. Copy. Let me move it in here. Insert, page, after, edit, paste. Ta-da! Okay, here we go. There's a different kind of, you got hybridization going on here. So these, don't worry about what these bonds are doing. You can treat them as sigma bonds. But look at the p orbitals are above and below, and they can link up parallel. So there's something about the parallel. Okay. Pi bond is that parallel overlap of p orbitals. Okay, question. Create a graph using the bond dissociation energy and the bond length data and describe the relationship. Basically, as the energy gets higher, the length is shorter, like in a triple bond. As the length gets longer, like you have in single bonds, the energy gets less. Predict the relative bond dissociation energies needed to break the bonds in the structures below. The acetylene there should be pretty high, the ethine. Carbon-carbon bonds take more energy to break than carbon-hydrogen bonds. In both cases, the carbon-carbon bond takes more energy to break than the carbon-hydrogen bond. I just think that's a weird way the question is worded. Okay. Name the compounds on number 14. Okay, this is a little different from the naming we focused on last year with the ionics. Last year what we did is we learned how to do ionic bonds, naming ionic compounds and writing formulas for ionic compounds. We did this in here with a couple weeks ago with a worksheet. We did that last year. That worksheet came from last year. But we also did, on some kind of an odd day after a test and it was bonus or something, binaries. This year we're going to focus on binary compounds more. Molecular compounds more. Organic chemistry, it's almost all molecular compounds. These covalent. The naming is a little different because you have dis and tris and tetras and pentas in these. You don't have those with ionic compounds. So you name the first element, it's still two names, the first name and the last name. The first element is the least electronegative, farthest from fluorine. As you go, your elements get closer to fluorine, as a general rule. The second element ends in "ide" if it's binary. Now that's like ionic, those end in "ide" if it's binary. The difference is you have prefixes, and by the way, this is not stock system naming. This book, for whatever reason, doesn't do oxidation numbers till forever later, but there's a stock system naming where you do it by oxidation number. That's not today. So there's two naming systems for this. And you need both of them, unfortunately. You have to have prefixes that indicate the number of atoms of each element. So some common prefixes are: 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 hexa, 7 hepta, 8 octa, 9 nona, 10 deca. Be familiar with those. So if you go, for example, to name this one, it's carbon dioxide. And the next one is sulfur dioxide, because you have 2 oxygen, so it's dioxide. 2 oxygen, dioxide. NF3, nitrogen trifluoride. CCl4, ask me about it when you come in here. I'll let you have a sniff of this. I've got some carbon tetrachloride. Okay. And diarsenic trioxide is 2 arsenics and 3 oxygen. So what happened here? Okay, so that's what you have on that. And then the next section, they probably give you names and have you write the formulas. Not real sure. Yeah. Going from (19) and 20, you got naming on the next. Oh, that's some acid stuff on the next one. I honestly don't like the way they do this because they're all over the place on this. Let's try these. Name these molecular compounds. We're going to find something that doesn't work here, I bet you. Nitrogen dioxide, dinitrogen monoxide. I have to give the 1 here, and we didn't give the 1 anywhere else. Why? Well, I'm not going to deal with that rule today. There is an addendum to the rule. Nitrogen trioxide, dinitrogen tetroxide, dinitrogen pentoxide. These are not in the book. But this is a great example to point out the other naming systems. So we're going to return to this when we get to stock system naming and oxidation numbers. Okay, so acids. Here's the good news on acids. The good news is you can pretty much get by with knowing these 5. Okay, you got hydrochloric, phosphoric, acetic, nitric, sulfuric. Now, that's easy because if you know chlorine is Cl, and this is the phosphate ion, so it's phosphoric acid, and this is acetate ion, so this is acetic acid, and you know this is the nitrate ion, so it's nitric acid, and you know this is a sulfate ion, so it's sulfuric acid. That's easy, and these are the acids you're almost always using. So that's the good news. Okay. So there are 2 kinds of acids. It could be something off the periodic table on that side, like hydrofluoric, hydrochloric, hydrobromic, hydroiodic. And the way you do that is you got hydro, and then the element, and then ic, acid. If it's made out of a polyatomic ion that has oxygen in it, like carbonates, sulfate, there's 2 things you got to pay attention to. If it's got a per or a hypo, you keep that. But if your anion ends in ate, like carbonate, sulfate, phosphate, the suffix becomes ic. If the name of the anion suffix is ite, like sulfite, chlorite, you replace it with os. O-U-S, and the second name is acid. So, something didn't get saved. Okay, tell you what, I'll pick up with that later. So the next thing for you to do is continue in the questions from page 251. This is where I'll cut it off for